Welcome back to the MS Portfolio. This is episode number 9, covering trigonometry. This is an episode that has been eating my hard drive because I've messed up so many times. Let's start with the basics. SOHCAHTOA. Sine is equal to the opposite over the hypotenuse, cosine is equal to the adjacent over the hypotenuse, and the tangent is equal to the opposite over the adjacent. Let's quickly take a look to see how this can be applied. First, let's try to find the side length y, because we are trying to solve this triangle. Ooh, that's a rough E. But, of course, we can do this by finding angle y, which is equal to 31 degrees, finding its sine, which is going to be sine 31 degrees, is equal to y over 52. Of course, that's the opposite, which is angle y, over the hypotenuse 52, which gives us y is roughly equal to 26.8 centimeters. Next, we want to find the value of angle x, which is going to be equal to 180 minus 31 minus 90, because there's 180 degrees in a triangle, minus our y angle, minus our right angle that we have, because, of course, all of the triangles that we are going to be looking at in trigonometry are going to be right triangles. And using that, we can see that 59 degrees is the value of x. But to solve it a little bit more trigonometrically, we can look at the cosine, or the inverse cosine rather, of theta, which is the same as our x here. So we can just try to find the inverse cosine of 26.8 over 52. We are using the inverse because we are looking for an angle and not a side length, which gives us the same value of 59. And then lastly, we're trying to solve for our side length x, which is much of the same as we did in this first little bit here, where sine 59 degrees is equal to x over 52, which gives us x is roughly equal to 44.6 centimeters. Here's another example. Here we are looking for the value of theta right here, but first we have to find the value of x here, because our theta value is our g value, which is this whole angle, minus the x value. And we have to find the x value first, just because we don't have enough information for value of theta. So, same principle as our value of x in that last one, where x is equal to the inverse tangent of 8 over 19, of course, just the opposite over the adjacent, which is roughly equal to 22.83 degrees. And we can do the exact same thing with our g value, but only add this 5 to the numerator, because we are looking at the full triangle. In this first part here, we were kind of just ignoring this, but now we want to know the value of the full triangle, which is going to be the inverse tangent of 13 over 19, which gives us a value of 34.38 degrees. And then we just find our theta by taking our g value and subtracting our x value, and then rounding to the nearest degree to give us about 12 degrees. Next, I want to take a look at different names for angles. Here we have angles that are much of the same. They are coterminal, which means that if you subtract 360 from one of them, in this case it's the 405, minus 360, you will get the same number, 45. It's a bit of a rough 5, but there you go. And the only real difference between these two angles is the principal angle, which is just the number you see here, which is all of that. And then the principal angle for this one is just 45. And just because they have the same related acute angle doesn't necessarily mean that they're the same. If I draw a line here, which is 270 degrees, this would also be 45 degrees, giving it the same related acute angle, but naturally 270 degrees and 45 degrees are not the same angle. So let's take a look at how we might look at a triangle on a graph. Here we are trying to find the sine, cosine, and tangent of theta, which we can do pretty easily using the Pythagorean theorem, which is of course a squared plus b squared equals c squared, where a squared is 6 squared, b squared is negative 5 squared, and our c squared is the same as our hypotenuse squared, because c is our hypotenuse. And we can look, it's the same as we're doing up here. I'm just going to rewrite it. 36 plus 25 is equal to our hypotenuse squared, which means that our hypotenuse is the root 61, which now we have all of the side length values, which means that we can solve the sine, cosine, and tangent. The tangent, we don't need the hypotenuse for, it's just negative 5 over 6, but our cosine and sine are both over our hypotenuse, and then of course this is 6, which is our adjacent angle, and negative 5, which is our opposite angle. Next, we have another example where we are given a point K6 and told that it is 10 units away from the center here, meaning that our hypotenuse is equal to 10 and our opposite is equal to 6 because we have the y value 6 here. And we are left with the variable k, and we're going to have to solve for that. This is done pretty easily, again, using the Pythagorean theorem. A squared plus b squared is equal to c squared, only this time we already have the value of c squared, which is 10 squared, and we're going to take our 6 here and count it as our a value, which is 6 squared now, plus k squared. Now we can rearrange this as k squared is equal to 10 squared minus 6 squared, which means 100 minus 36. So k squared is equal to 100 minus 36, which means that k is equal to 64, or k squared is equal to 64, which means that k is just equal to 8. And now we can see sine is equal to our opposite over our hypotenuse, which is just 6 over 10, which can be simplified to 3 over 5. Our cosine is equal to k, or 8 over 10, which is just equal to 4 over 5. And our tangent is equal to our opposite over our adjacent, so our opposite 6 over 8, which can be simplified to 3 over 4. Next, I want to look at the significance of the sine and cosine multiples of 90. So first, let's take our sines. This is sine 0, 90, 180, 270, and 360. So these are all super easy to remember if you just remember them as a wave function, which we will get into in the next part, I believe, where all of these values can be shown. Of course, sine 0 equals 0, sine 90 equals 1, sine 180 is 0, sine 270 negative 1, and sine 360 0, of course, because 0 and 360 are coterminal. Now let's take a look at the exact same thing with our cosines. Probably should have wrote these down beforehand, but it's fine. So cosine 0, cosine 90, 180, 270, 360. And it is the same thing, except shifted a little bit, where our sine 90 is equal to our cosine 0. So cosine 0, we're going to start with the 1, and then we go down to our 0, -1, 0, 1. And we can see here, if we extend this just one more thing here, 0, -1, and 0, that our cosines are the same as our sines, only the sines are shifted 90 degrees to the right. And now, next, I want to look at our easy little squares that we have here. Or not squares, triangles. It's the whole point of trigonometry. But these are very easy to find when you know these values of 60 and 30, and then 45 and 45. So for this first triangle, sine 30 is equal to the opposite over the hypotenuse, which is 1 over 2. The cosine is equal to the adjacent over the hypotenuse, which is going to be root 3 over 2. And then our tangent is going to be 1 over root 3. And now for our other angle here, we have sine 60 is equal to our opposite over our hypotenuse, root 3 over 2. Our cosine of 60 is going to equal our adjacent over our hypotenuse, which is 1 over 2. And then our tangent is going to be our opposite over our adjacent, which just gives us root 3 because it's over 1. It doesn't make a difference. And now moving on to this last triangle, we have the sine of 45 is equal to 1 over 2, of course, or 1 over root 2, rather. And then our cosine is going to be the same thing because our opposite and adjacent are equal. And then lastly, our tangent is going to be 45 degrees, or our tangent of 45 degrees, rather, is going to be our opposite over our adjacent, which we already know are equal, so it's just 1. And so when you see any of these values, 30, 60, or 45, you can just draw these triangles out pretty easily and be able to tell the exact values.